For decades, the whole story around nuclear power has been about cost. It's too expensive, it's too slow, it's just too darn risky. But what if that entire story is based on an incomplete picture? What if the key to our clean energy future has been hiding in plain sight this whole time? Let's dive into some fresh analysis that really reframes this entire debate.
Okay, so think about this. We are heading into an era of absolutely unprecedented electricity demand. We're talking about massive data centers for AI, charging stations for electric vehicles everywhere, and this huge push to electrify everything in our homes and industries. And here's the thing, this demand isn't a nice to have. It needs power around the clock, 24/7.
Right, so we've made some incredible progress with renewables like solar and wind. They've delivered huge amounts of clean energy, which is fantastic. But they have a fundamental limitation, one that keeps them from solving the entire puzzle on their own.
And that missing piece, it's what we call firm power. It's literally the foundation of our entire grid. The power that is always on, keeping things running when the sun isn't shining and the wind isn't blowing. For a modern economy, this isn't just a bonus, it's absolutely essential. So you'd think this is where nuclear power would just shine, right? It's clean, it's firm, but yeah, it has a reputation, and let's be honest, for good reason. We've all seen the headlines about these massive budget overruns and delays that stretch on for a decade. And yeah, there is no better, or maybe I should say worse, example than the VALCOE plant down in Georgia. The final price tag just ballooned to over $30 billion. That's more than double the original estimate. It's no wonder this single project became the poster child for everything that can go wrong with building nuclear.
But here's the twist. What if VALCOE isn't really a story about bad tech, but just really, really bad execution? Just look at this checklist. It's fascinating. It lays out what leads to success versus what leads to failure. And you see the high cost column? Lack of a completed design before you start building, supply chain chaos, treating it like a one-off project. VALCOE checked pretty much every single box. The big takeaway here is that these are project management failures, not some fundamental flaw in nuclear physics. Okay, so if the real problem is how we build these things, maybe the way we measure their value is messed up too. And this is where the perspective really starts to shift in a big way.
Let's really dig into that question. What if the very tools we've been using for years to compare energy costs have actually been hiding nuclear's true worth all along? So, for years, the go-to metric has been something called LCOE. The easiest way to think about it is like the sticker price on a car. It tells you what it costs to buy it, but it tells you nothing about the cost of gas, insurance, or repairs, the total cost of ownership. LCOE is the same. It tells you the cost to make a unit of power, but it totally ignores all the other costs a source might put on the grid, like needing backup power or brand new transmission lines.
All right, so the first new tool to talk about is called the Value of Early Power, or VOE. It's kind of like this. Imagine you're opening a restaurant. Does it make more sense to open right before the big summer tourist rush or a few months after everyone's gone home? Of course you open early. Getting a power plant online sooner captures a ton of value. Speed is money.
And we are not talking chump change here. This analysis shows that just getting a big nuclear plant online 5 years earlier is worth about $2 billion. What this really drives home is that a good enough plant that's actually built now can be way more valuable than some perfect plant that gets built 10 years from now. And that brings us to the second tool, and this one's a big one, VALCOE. Think of this as the total cost of ownership for electricity. It basically takes that old sticker price, the LCOE, and then it adds in all the other costs, things like adequacy costs for backup power, balancing costs to keep the grid stable, and grid costs for new infrastructure. Finally, we have a level playing field.
Okay, so now we have these smarter ways to measure value. How do we actually fix the building problem? Well, the answer is a pretty fundamental shift in strategy. See, for way too long, we've been building nuclear plants like they're one-off, bespoke art projects. Every single one is a unique, high-risk venture, which means we never really get better or faster. The game changer is moving to what's called a fleet model. You standardize a design, and you just build them again and again and again. That's how you learn. That's how you drive costs down. And this whole idea is powered by a really powerful economic concept called the learning curve. It's just this simple observation that every time you double the number of things you've produced, the cost for each one drops by a predictable amount.
I mean, this isn't some crazy theory. It's the very reason solar panels and wind turbines got so ridiculously cheap. Nuclear just, well, it never got a chance to ride that wave.
All right, let's put it all together. We've got a better way to measure cost and a better way to build. So what happens when you combine them? This is really the aha moment of the whole analysis. When you finally stop building these one-off projects, you start building fleets, and you measure the full value using this VALCOE metric, well, the numbers start telling a very new and very surprising story.
And boom, here it is. By the 2030s, the total system cost for nuclear, its VALCOE, drops into a range of about $87 to $99 per megawatt hour. Just look at the other options here. That puts nuclear head-to-head with other big, clean, firm technologies like geothermal or solar farm paired with 12 hours of battery storage. All of a sudden, nuclear isn't the expensive outlier anymore. It's right there in the mix.
So how do we actually make this happen? Well, the analysis lays out two really smart, complementary paths. First, we can use the proven large-scale reactors we already know how to build and get them online sooner to capture that massive value of early power. And second, we can invest in the new small modular reactors, or SMRs, which are literally designed to be built in factories and ride that learning curve down even faster. So first, let's look at the big guys, the large reactors. If we just commit to building one new plant a year starting in 2030, which is a pretty moderate pace, the total system cost drops steadily. It goes from $112 all the way down to a very competitive $87 by 2045. That right there is the power of just building the same thing over and over. You get better, you get cheaper.
Okay, now for the small modular reactors. The really cool thing here is that they actually start out more expensive at $139. But because you build them in a factory, they learn much, much faster. In a similar scenario, their costs just plummet, hitting $90 by 2045. So they start out a little behind, but they catch up fast. A different road, but they end up in the exact same place. Cost competitive. So if the tech is solid and the math actually works, what's the real roadblock here? What's the thing we really have to overcome?
This one quote from the analysis just hits the nail on the head. Execution discipline matters more than reactor choice. What this is really saying is that our future success with nuclear isn't about picking some perfect, magical reactor. It's about getting really, really good at building things efficiently and consistently. And that really is what it all boils down to. The analysis makes a powerful case that the technology is there and the economics can work. It's not a science problem anymore. It's an industrial problem, an organizational one, a human one. So the real question isn't whether nuclear can be a solution. The real question is whether we are ready to execute.